Hello, everyone. Thank you for joining. As was mentioned, my name is Dmitry, and today we'll talk about concurrency with a particular focus on asynchronous programming. But obviously, first, we need to be very clear on our goals, so you can actually figure out maybe the talks next door is much more appealing. So the goals for today are quite clear. First of all, I really like to highlight the concurrency as a whole and just different forms and shapes it comes in the industry. Then I'd like to highlight a couple of the misconceptions that cause people to avoid concurrency at all costs and ultimately try to debunk them. And we'll wrap up this session by talking about the asynchronous programming and try to implement use of workflows in Java. So, obviously the good question to ask first is, why do we want to have to talk about it? Why the concurrency? And obviously you've been asking that question for quite some time. And everyone knows that the multi-core as the principle is quite a standard these days. Even the laptop I use today has multiple cores in it. So there's not even something to discuss. We all agree that almost every machine these days has a couple of them. The microservices are so abandoned these days that it's not even a buzzword anymore. You can't even surprise anyone at the conference to talk about microservices. And obviously the computing cloud services like AWS and Azure are driving half of the internet these days. So you can't avoid them either. And obviously, if you talk about concurrency or any sort of IT development, you have to mention the Moore's law, which some people debate whether it's still alive or not. Regardless, it just shows that the world is changing quite drastically, and you have to admit that concurrency is a new reality, and I would even say it's been a reality for quite some time. But honestly, you can still argue, yes, the world is changing, but what's in it for me? Like, why do I care? You can still argue against it. And obviously, there are some benefits. The first benefit is obviously the fact that since we have so many resources, like the multi-core environments and the computing cloud services, not using those resources is wasteful. They're just going to idle there. You would like to really improve the user experience. These days, users are quite picky. They have the perceived performance of the apps, which is just under like 2 seconds or about 1 second. And if you really want to have a good user experience, you have to have concurrency in place, some multi-threading going on. And obviously, what I like about concurrency, regardless of your app itself, that it really forces you to have a better abstractions and try to cut off all that fat, all those complexities as much as you can, because the concurrency by itself is fairly complex. And as I just mentioned about the complexity of concurrency, you can't just talk about concurrency as a whole without mentioning the complexities. It's not just the good parts. And the complexities are quite clear, and everyone, I would say, knows about them to some extent. Obviously, it's the problem with thread safety. When you have resources shared across multiple threads, the states they're in can differ drastically. Obviously, the liveness, the thread starvation is a common problem, and the term you probably all heard of, the race conditions, all of those. The performance is actually something I really like to point out, is especially for the managers when they think that if you have a single-threaded app and you just make it multi-threaded, it's not going to performance not going to improve 2-folds or 10-folds. You really have to tune it for your specific use case. And of course, the concurrency as a whole really affects the entire software development lifecycle, starting from the design, development, and all the way to testing. So everything is affected to some extent, hence people have to be retrained, people have to learn how to work with it, tips and tricks. So complexity is there, of course. So we have to admit it's complex, as I've mentioned, but at the same time, as I highlighted before, it's beneficial. And I would even go further and say it's beautiful to some extent. And you can think of, if something is so complex that it kind of scares you at first, but at the same time it's beautiful if you learn about it more, you might think of something else that it reminds you of. And what I like to compare concurrency to, personally, is that this guy, the sharks. To me, concurrency is very much like a shark. And the way to really describe it the best, to illustrate it, is just by looking at these two guys, these two books. First one is obviously the Concurrency in Practice by Brian Goetz. If you ever open it, especially the first couple chapters, if you've never touched concurrency before except threads and runnables, you're really faced with that idea that nothing is certain, the time and order don't exist, and you freak out at first. That fear of concurrency as a whole really shocks you. The same comes with sharks. You think of sharks to be, predator, very dangerous, they're gonna eat you alive if you just go for a swim. But if you actually learn about them, you know how fascinating animals they are, and you start admiring them. And I would say this is the main problem we'll try to solve today. So we'll try to go from this fear to the admiration, not about the sharks, but about the concurrency. So this is where we're gonna focus on as a whole for the concurrency and also for the asynchronous programming in Java. So you guys don't really stay away from it. And of course, to talk about it, I'd like to draw the agenda. I like to draw it as like kind of a map, so we go on a journey for this admiration path, you can call it. We'll start with the single-threaded applications and how concurrency come into play in that environment. Then we will move on to the multi-threaded environment, obviously. So far, this top level will be language agnostic, so it's regardless of what language you have in place, whether it's Java, Python, Go, whatever. And then we'll go to, obviously, it's Java conference, so we'll talk about concurrency in Java. And ultimately, we will discuss the workflows in Java. Even though we'll look at other languages, how they handle it as well. Okay, so it's 11, correct. All right, so let's start with the single-threaded environments. As I mentioned before, the world is changing. You can still argue against the change and stick to your plan. I've heard in the past things like, my app is single-threaded, why do I care? You can say concurrency is way too complicated, or that common approach people take when they say, if it's not broken, don't touch it, especially if it's a legacy system, which is fair to some extent. You always have to evaluate the return of investment, but that's somewhat a dangerous path to take. You have to be open to the innovations. Especially as I've mentioned, the world is changing so rapidly. So, what I like to bring up is something called design for concurrency. I really like that concept. Obviously, many other speakers and authors talked about it quite in length. Ideally, you can apply these principles regardless of what environment you're in. Hence, I'm talking about design for concurrency in a single-threaded environment. In a way where you're trying to avoid at all cost programming by coincidence. You don't just implement something and assume it's going to work, or that famous meme on the internet where they say, it works, I don't know how, I made it work, I have no idea how I made it work. So this kind of ideas you really should avoid and go towards something that I really like to tackle this problem by using design by contract. It's a very neat concept. The idea here is that you try to interact with your code and with people in a way where, the same way you would interact with people in a real life. For example, if you have an employment contract, in an employment contract you have stated your responsibility to do the work, and you have the right to get paid by your employer. The same way you write your APIs and your code, because the code itself, the high-level languages, it's all about not communication with the computer, it's about communication with the engineers. Hence, the design by contract takes it one level above and really forces us and give you some guidance on how to implement those contracts. You're basically trying to define your responsibilities as an API owner and your rights as if you are an API consumer. So this is what the design by contract is. Obviously, the temporal coupling is another anti-pattern you try to avoid, and it's especially important if you're working in concurrency. Again, as I mentioned, we're talking about this in a single-threaded environment. First of all, it will improve your overall architecture, and also it will prepare you for possible move to the multi-threaded environment in the future. So the temporal coupling, the way I'd like to describe it, it's, again, as I've mentioned with the concurrency book, that it really highlights that order and time don't matter anymore as much. You can't assume that it's going to just be executed from top to bottom. The temporal coupling, the way it works is the order of operations affects the state of your class, of the instance of your class. So, for example, it's the frequent one with the HTTP requests that you can make. If you make the request itself, only then you can fetch the data from that object. So if I were not to execute that request beforehand, and I try to get the body of such request, it would be empty. So basically, it's the order of operation that dictates the state of your object. That's what the temporal coupling is. And you try to tackle it by, you can tackle simplistic things like immutability and atomicity that you try to implement And obviously, we all know what it is, and we all know why this is good. So I'm not going to talk about this too much. What I'd like to focus today is the multi-threaded a little bit more. And when you talk about multi-threading, there are a couple of shapes and forms it can take. Especially these days, when with so much data online, you can get confused. And this is one of the versions I've used in my practice. And so first is the concurrent form people like to talk about. Then it's a parallel form, and obviously the asynchronous form that we will be focusing on today. So let's get started with the concurrent form. Just in a couple of bullet points, it's the idea is such: you're trying to have multiple tasks, obviously, but they are logically simultaneous. What it means is that they don't require multiple CPUs in place. So you can technically run this concurrent application in a single CPU environment, which obviously is not going to be a problem these days, because we all have a couple. But the idea is, it makes it seem like it runs in parallel, but it doesn't in a single CPU environment. So if you were to just look at the small diagram, it will be like you're trying to run a couple tasks in parallel. Honestly, I don't like these abstractions, these diagrams. I like to be more practical. And when it comes to being practical, obviously you have to set the use case. So imagine we're trying to develop an app in our workplace. And you have a guy named John who needs only two things to develop an app. First of all, obviously, he needs coffee. You can't develop an app without a coffee. And the second of all, he actually needs a laptop. So John got both of those. But the thing with John, though, he only has one point of focus. Think of this as being a single CPU. Or think of this as John is the guy who can only do one thing at the time. He can drink the coffee, then he puts down the cup, he grabs his laptop, he does the coding, then he puts down the laptop, drinks the coffee, and so on and so forth. Ultimately, there were two tasks: to drink the coffee and to basically code the app. He completes both of them at the end of the day, but it seemed like he finished them in parallel, but at the same time, he had to switch back and forth between them. So it's kind of a stretch, but I hope I were able to describe it to some extent. As I go to the different forms, maybe it will make a bit more sense. So obviously, if you go to the parallel form, it's a bit more complex and more advanced in the sense that it's multiple tasks, or some people even call it subtasks to some extent, and it has to be physically simultaneous tasks in the sense that it does require multiple core CPUs in place. People, again, as I mentioned, the subtask, meaning that you have a single goal in mind, and you're trying to split it into subtasks. After they're done, you combine the results, and you finish your main task. So, if you again were to look a bit more practical on our developing app situation, now we have someone called Jenny. Jenny, she's amazing. What she does is, obviously, she still needs coffee, she still needs her laptop, but she's ambidexter. Ambidexter people, they can use their hands in isolation, like in the same time. So Jenny can have one line of focus and a second line of focus, where with one hand she can keep drinking coffee, and with another she can just go with it and just develop an app. So at the same time, she can do both with no interruption. And ultimately, she completes both tasks in parallel, but you need to have 2 points of focus. And ultimately, she develops an app. So that's what parallel comparing to the concurrent form would be. And obviously, as I've mentioned, the last but not least is a synchronous form. That one is a bit more advanced, you can say, but very useful. It's trying to follow the fire and forget pattern, where you have a major thread in mind, like major concept in mind, and you trigger a side process that doesn't necessarily affect your major task at hand, but you still would love to know whether it failed or succeeded. As I've shown here, it has to be non-blocking, and because again, as I've mentioned, it should not be interrupting your main task. And at the same time, of course, it requires multiple CPUs because it has to be non-blocking. The good example would be, imagine you go into the ATM to withdraw some cash, and as a customer, you're withdrawing the cash, and maybe there is a synchronous task by the ATM to send the information to the Splunk to log it. And if a Splunk instance is down, I shouldn't be prevented from withdrawing my money. So that Splunk login process is a synchronous process that was triggered by the ATM, and the main task at hand was for me to withdraw my money. So think of that. I forgot how that happened. and I don't want that thread to block me to move forward. And going back to our developing app situation, we're back to John, and John, as always, just has a coffee and a laptop. But now a good question to ask, he fortunately asked it at some point, where does the coffee come from? And coffee obviously comes from the coffee machine. And imagine he has a colleague, Henry. Henry is a great guy. What the Henry does, it's while our guy, John, keeps developing the app, drinking coffee, working on his code, Henry would keep making coffee over and over again. He's made so much that he's not blocking John, but John still cares about the coffee being made. So that's kind of a stretch, but I'm trying to highlight that. While John is not blocked for his main task at hand to develop an app, he still kind of needs Henry to do his work as well. So that's basically to highlight the different forms and shapes of multithreading. I hope it was to some extent clear. Going to the concurrency, here is the interesting thing though, especially in Java, concurrency, because before I've been talking about language agnostic concepts. Now as we go to Java, frequently people say concurrency and they just imply all of those shapes and forms I just mentioned. They would say concurrent, parallel, async, and they would all call them concurrency. I would try to keep it clear, but right now I'll just talk about the concurrency in Java as a whole. And obviously, as we all know, what was first in Java for concurrency, it's runnables and threads. And honestly speaking, this one part of the problem. I would even say it's maybe the core of the problem, that people avoid concurrency at all costs because they got scared by using those two. Particularly so if you start with runnables, it's basically the unit of work for the threads. In a sense, it's people like to call it a selfish interface because it doesn't take any input, doesn't give any output, and doesn't throw any checked exceptions. And obviously, if you've done it before, you would see that, as I've mentioned, it's just a unit of work. You just implement the interface, you have the unit of work and the run method, and you go with it. And obviously, you can trigger run, nothing happens. It's just a synchronous flow of code. Runnables by themselves are useless. So here is where a thread comes in. Thread is what basically uses the runnable to be able to trigger that process that runs in parallel, asynchronously, or whatever you choose to do. So obviously with threads, they are runnable based. They also runnables, but you don't want to really do that. There's always at least one main thread in your app. And if you were to look at the actual code, obviously we've all seen this before. You would use composition, that's the best way to handle threads. You would send the unit of work in the constructor where the developer drinks coffee, obviously. And you try to run the thread, because thread, again, it's runnable. Nothing really happens. You have to start the thread. This is where magic goes on, and the new thread gets spun off and goes with it. One thing I have to mention, and this is where the fear of threads and runnables comes in, threads are difficult to manage. They have an overhead. For the creation, for management, for their life cycle, this is where it's fairly complex, especially if you have to use synchronization on your own, which you can get to be very bad performance, so you have to be very careful with those. This is what people thought, and they stopped working with concurrency at all. And this is where JDK 5 came in, that was released, which is a great thing. I think it was September 2004. When it was first released, and it brought us concurrency API. Great piece of software, great API in the sense that it brought lots of features. Some of the ones we'll talk about, I think are, can be more mainstream. They actually are. So it's a ThreadLocal, the atomic operations, obviously the thread-safe collections, and a lot more. We'll only talk about these three, unfortunately, due to time. So the ThreadLocals. ThreadLocal is an awesome class. So what it does, it basically does the resource confinement for your multi-threaded environment. As I've mentioned, one of the problems with multi-threading is the resource sharing. So if if multiple threads at the same time access the same instance of the class, and that instance is mutable, God forbids, they would change that object state and try to reuse it. And as a result, one thread would affect another. There is nothing worse than when you don't have consistency in your app and you have one thread affecting another. It's the worst thing you could do. And so the resource confinement, the way it works, It's basically, you can think of it as key value pair for your resources, where a key is a thread and the value is an instance of a class. So in a scenario here, the simple date formatter, as you can see in this code sample, it's a very famously known thread unsafe class in Java, in older packages. And so the idea of ThreadLocal, what it does, every time a new thread comes in and tries to use it, it would basically instantiate a new simple date formatter for that thread. And whenever that thread comes in, it's that instance that will be served. So it's isolated to that individual thread. Obviously, it doesn't come for free. There's some memory leaks that you can possibly have. Again, those resources have to be managed. And it really might encourage you to go with the anti-patterns, like having lots of global fields, which is generally a bad idea. As we all know, global fields have rules behind them. It's hard to manage them for concurrency, and just for any design, you try to avoid having global fields unless they're used in every single method in your class. But that's a different topic, of course. So, in terms of the atomic operation, that one is interesting, because it's trying to tackle a problem that you don't really think of at first, especially if you're in a single-threaded environment for so long. It's the idea of compound operations. So even if you know the inline incrementation, you know that I++, it's actually not the single operation. It's not thread safe. Because the way it works, it has to get the value, incremented by 1, and reassign back to the variable. These are 3 operations. And because it's, as I mentioned, with concurrency, you don't know what the order will be like, what the time will be like. Anything can happen between those 3 operations. So compound operations is the ones that consist of multiple steps. The atomic operations allow us to really increase the speed of handling those operations, because in regular flows, you would have to synchronize those variables, which would be very, very complex to manage if you haven't done it in the past. And obviously, they use something called compare and swap behind the scene, quite a nice algorithm. But if you look at the example, as I've mentioned that I++ scenario, as you see in one of the comments there, which is not thread safe, if you want to do it in a thread safe way, it will be just a single line using this atomic long. If you were to do it synchronization on this variable, using the pre-JDK 5, it will be very lengthy, very verbose, and let's admit, Java is verbose enough. So, obviously, it goes beyond just the counters. You can do the references if you'd like. And in terms of the thread-safe collections, which are obviously, we work with data most of the time, so we in most of the data in some sort of a collection. So, of course, it really comes handy quite often. And the thing is, there are quite a few collections. I'll focus on the one, probably the most famous one that people use the most. It's concurrent hash map. Of course, it's still trying to tackle the problem of compound operations, because when you check the collection for a value, then getting the value and then setting it back, that's obviously not thread-safe operations that you have to manage on your own. These thread-safe collections allow you for better speed, and they also allow you for configuration, for concurrency configurations as well. So to look at the use case, if before you would have just a regular hash map, you would have a regular hash map, and you have a scenario where you try to count how many times a certain process was triggered. So you basically say, you have a simple method, increment by process ID. So you pass the process ID, you have to do that synchronized keyword thing. Synchronized keyword, what basically means 2 thread comes in, if one is using that synchronized block, another one just has to wait, idle. I'm kind of simplifying here, but that's the gist of it. So you, again, idling of resources is something you really try to avoid. Concurrent hash map, however, does some magic in there. And the magic that it does, it's that simple. You only have to, in this scenario, it basically has very nice methods, not just put, but like put if absent, and then you can send out the atomic log. I think it's atomic log in this scenario. Yes, atomic integer, regardless. You get the atomic integer, again, all these operations now are thread safe. I increment it. Because it's by reference, it also updates the value in the map. And if you were to compare the two, you would see how much less verbose, and as a result, much easier to manage and update and maintain. It's all about lowering the cost of maintenance. And it really goes down pretty drastically, if you were to ask me. So that's basically the concurrency in Java. And now, for the last part of today's talk, I really like to talk about something that really excites me is the workflows in Java. So obviously, good question to ask, where do we start? And the good place to start, of course, is looking at other workflows. And hence, we will talk about the workflows in JavaScript, or as people like to call them, promises. We will discuss the features and callables in Java. Then we will move on to something called Executor Framework, and we will obviously have to mention CompletableFuture. Otherwise, the talk won't be called CompletableFuture. So, starting with the promises. With JavaScript, it's interesting, because before they would have something, you probably all heard of the word callback hell. So before, imagine you have simple method, simple piece of logic, fixing the bug. And the thing is, you have to violate the single responsibility principle if you were to do the JavaScript old way, where you have the operation itself, and you also have to handle the operation result in the same method and perform different operation depending on the result. For instance, in this scenario, you're fixing the bug. If bug was successful, you call a function on success. If a function failed, you call a function on failure. So the abstraction becomes quite a useless one, sorry. And obviously, you would have to call it kind of this way, which again is you polluting the logic here. So but fortunately enough for the JavaScript guys, they implemented something we would call promises. The idea is here, you're really keeping the abstraction quite neat in a sense that you say fix bugs only should be fixing the bug, only should have that operation. And then depending on the operation result, it would go one way or another. So that's a smart workflow kind of logic, meaning that you've done your work, then the next guy in the chain would handle the failure or success. So that's basically the quick overview what they had. In terms of Java, so if runnables were the unit of work for threads, callables are unit of work for futures. So if you look at callables a little bit closer, callables are much nicer than runnables, in a sense that although they still don't take any input, they at least give us the result, they give us the output, and they give us the checked exceptions, which is a bit nicer way to communicate with the API. And if you were to look at an example, of course, you would have something like fixing bugs sometime in the future. You make a different call, it's not run, and it of course returns the whatever you choose it to be, and throws an exception. So that's a bit nicer than runnables. Of course, quite a few years passed between them. If you were to compare to the JavaScript example, you can do similar things. You get the result, and you handle it depending on whether it was success, failure, or exception. So again, that's simple. Honestly, this execution is, again, synchronous. We don't really care about it as much. If you were to look at futures, futures are a fun one. The way futures work, of course, they are completed in the future, ideally. And they are relying on something called Executor Framework, which we'll talk in great detail. I mean, in some detail, I would say. But for now, just roll with me on this one. Basically, you have something called Executor Service. As I mentioned, we'll discuss that. Imagine you have something that people promise to do the most in the future. It's actually fixed the to-do in code. So you say, in the future, my callable, I'll fix this to-do sometime in my code. Then what you do, you say service.submit, and you send that piece of work into the executor service. And at the moment where you it gets to the submit part is when the execution gets started. It's not blocking in that time. It only blocks when you do the get, which I'll again talk about in a second. But at least the gist of it is that now you can kind of get into this asynchronous fire and forget pattern, because on the submit time, it starts execution, it doesn't bother us anymore, so technically the next line can be executed in separation from this main logic. And of course, Future sounds kind of great comparing to the threads, but how do we actually use it? I've kind of mentioned it, of course, the executor service, and of course, this is where the executor framework comes in. And you cannot talk about the asynchronous development without the executor framework. So the Executor Framework, this one is actually great for tackling our main problem today, going from this fear of concurrency to the admiration, because it tackles thread management. It's a great help in a sense that it's really trying to have this declarative model in Java, to keep pushing that, because now you don't have to think about, after the thread is finished its work. As I've mentioned, the thread overhead for the creation is just non-existent. It's quite a big one, especially on the scale. So Executor Framework will handle management of those threads and the reusability of those threads. It will handle the creation. It will handle how many threads you can have at the time. So switching between tasks. And in terms of the framework, it's fairly simple in the diagram-wise. We would only focus on the two main parts, the thread pools and the executor service itself. So when you talked about the thread pool, that's actually the core of this framework, because this is the one that does thread management. And it also does the thread configuration, things like name of your thread, especially again if you are really logging a lot of information, you really need that to be able to distinguish between operations. If you were to look at actual Java code in the Java packages, you would see enormous number of arguments that make me cry every time I see that. 6 arguments, it's way too many arguments. But if you were to look at them closer, you can define how many threads you can have, how long they're gonna live for after they're done with their work. You can change the naming, you can change how they're stored, and so on and so forth. So again, it's way too many arguments, but not to worry. Fortunately, we have factories in the Executor Service. And they really put their time on developing those. And so with these guys, the Executor Factories, the first one that people use is a single thread pool. I like to start with that one whenever I do some POCs or just try to experiment, because you develop your app preparing for the multi-threading environment, but if you still use a single thread pool, it still uses only one thread. So as a result, it's much easier to test, much easier to develop, because first you always want to make sure that things work before you even go with optimizing them, right? So it's always a good place to start. Then there is a cached thread pool. Cached thread pool is a great thing for short-living tasks and when you don't really know how many tasks you will have. Things like the crawler service, if you were to make one, because you don't really know how many URLs you would have on a certain website. So, and obviously the crawling process hopefully is pretty short one, so that will be the cache thread pool. The fixed thread pool, it's when you know exactly how many threads you have. Those would be the long-running operations. Some math calculations, some search that you might apply to the certain arrays that you know of. There is also something called the schedule thread pool that you can use if you wanted to build your own, cron job, scheduler, or some monitoring service. Run this task on certain date, a certain schedule. And obviously the work stealing pool. That one is a bit more complex. It's that fork join pool that runs behind streams. They basically do a very good job between sharing the tasks responsibility behind the scene. And I won't be talking about this one too much. But so the executors and the thread pools, if you were to combine the two, you would get something called Executor Service. And this is what you use the most with futures. It's what you have to determine and trigger these asynchronous tasks and be able to use all the benefits of the thread pools, the thread management, the thread configurations, and so on. And so if you were to really develop a crawler service, as I mentioned before, you would have, you would define it, as I mentioned, the new cached thread pool. Then you would basically iterate through the URLs, and you would send the crawling data processing into the executor service, to the crawler service. So those are not blocking, so you can technically scan all of those pages fairly quickly. At least you will start the triggering the process. Obviously, then the collection of the data comes in, and this is what I'd like to talk about right now. It's that we're not, unfortunately, done yet with the executor services and futures, because future is not perfect. The problem with future is that it has quite a few pitfalls behind it. And one of those pitfalls, obviously, is the blocking operations I've mentioned quite a few times, but wasn't able to go into too much details. The fact that there is no real chaining of the results, unfortunately, so you cannot ever get real workflows. And the problem that you can't really combine futures, can't combine their data, the results. And the exceptions handling is quite poor with futures as well. So if you talk about the blocking operations, it's the idea that every get you make, not the submit operation, submit is asynchronous on the executor service, it's the get that's the problem. So if, for example, I say, crawl this website, and then I say, I can't wait anymore, I want to get the data now, and I just say, call get on the website content, that process can be just hanging there. It's going to stop everything, going to block the whole operation, and you also have to handle the exception here, obviously. That's bad, though. Don't ever, if you have to do it, don't ever do that this way. Always try to use a timeout. Like as you all know, the infinite loop is the worst thing you can ever have. I mean, not the worst, but one of the worst things. So you have a timeout, but still, it's still blocking. There is no real future chaining. Again, there is no workflows, which is a problem, of course. Imagine you have the team that works in a Kanban or whatever is agile you would choose to have in place. You have a developer developing an app. So while that app is being developed, you say entire team has to wait because you made a get call on it. You say program.get. So the entire team waits for this one developer. And only after it's done, after the code was produced, only then the testing can be done. But this is even more weird because now you call get on that testing code, and the entire even dev team is waiting on this tester. So if you just think this conceptually, how complicated that is and how useless to some extent that could be. Obviously, you can solve it going towards this callback hell. I'm not going to show that. Callback hell is bad, so don't even do that. So the future combinations is a nice thing that could be done, but again, it's blocking. The InvokeAny and InvokeAll, the frequent one that people use. Imagine you have an array of data, 10,000 random values, and you're trying to search for a single value. What you could do is to write two callables, 2 units of work, 2 different search implementations, linear and binary search, whatever you select to do. So you have those search unit of works implemented elsewhere, and you say, my executor service, invoke any of those. It will actually invoke both of them, basically, and whatever produces the result first, give it to me. Hopefully, both of these algorithms do the same kind of search in the sense that they will find the correct value both ways, but whatever will be the fastest one, that one will produce me the result. So you don't care which one, you care about the data that will be produced. So that's one of the nicer calls you can make in executor service, but still, that's a blocking operation, which is, again, not very useful. The exception handling is, again, it's about the developer's experience, the whole coding concept, right? And fortunately, in the futures, you have multiple exceptions in place on most operations. In average, imagine if you wanted to just log some log line to Splunk, you would have quite a few exceptions to handle, and all of them have to be handled in a different manner. You would have the interrupted exception, which you handle by interrupting the threads. You would have executor exceptions, which are a beast on its own, a fairly complex one, but I can chat about it after. And the timeout exception, obviously, you need to tackle in a certain way as well. So you can say, futures, they're so great, but so many issues. How do I even, why do I care then? Not to worry, obviously, there is a completable future in place, which is quite a great one. So with that, we'll go to the last part, the completable future part. And completable future, the way we'll describe it is first, of course, highlight what's useful about it. Again, it supports all those major, nice, fancy operations like transformation, composition, chaining, and combination. And it can achieve all of those functionalities by obviously implementing the future. So it has everything the future has, and a bit more by implementing the completion stage. So if you were to look back again at those pitfalls of futures, blocking operations, no result chaining, future combinations being absent, and the exception handling, if you were to handle them with a completable future, you can do things like, again, transform and chain the operations finally, in a way where you have actually workflows in Java. They mostly rely on the fork join pool in that regard, which again, I don't have time to talk about unless you really want to at the end. But the idea is, imagine again, developer keeps at coding, develops a new app, and again, you want to make a coffee. So you would do it this way, where you use the static factory of supply async on a CompletableFuture, and you start brewing coffee behind the scene without interrupting the developer's coding process. And only after that making coffee process is done, only when the coffee is complete, only then you can drink the coffee, while the developer is not interrupted from their main work. So this is the real asynchronous flow, and you can see that workflow I showed you with promises in JavaScript, where only after the coffee was done, the next guy in the chain, then apply in this scenario, only then we actually drank the coffee. So we didn't stop until the coffee was done. And when it comes to the completable future being controlled, it's much more advanced than the futures themselves. Now here you can actually complete them if you wanted to, a much better way, in a sense that you can have not just the timeouts like you would when you, as I showed you guys with the get with the timeout. Here you can actually, again, the use case, I'm making coffee. In this scenario, I'm trying to make a latte, but it's taking quite some time, and I say, screw with latte, just give me the Americano now. The way it would work is, if it's not done yet, I just finish the whole process, I set the default value, in this case, it will be Americano, and they'll give it to me. Or a different way I can handle it is by completing it with a certain value. In this case, I say, just give me the espresso, which is part of latte. Give me the espresso, I'll drink it now if you haven't finished the tasks yet. So you can see that you have much more control comparing to just being a timeout in place. So it's kind of a little bit more advanced. But what I really like is that now you can have multiple features control in a way where, not as I showed you before with InvokeAny and InvokeAll, you have something of all off or any off. Good use case that I've used in the past myself is if you're writing the WebDriver tests and you have multiple browsers to handle, you have the same test in place, but you run it with the different browsers. You can basically supply it to the all-off for Firefox, Chrome, and IE. The only, of course, the kind of downside of this method is, fortunately, it's not blocking comparing to the futures. But the bad part about it is that the results are not really formatted. As you can see, the result of this all-off would be the completable future of void, which gives us some information like, is it done with exception, how many are still in progress. Even though you can easily handle this situation by storing the references of individual completable futures in the all-off, but it kind of shows you that there is some improvements can be made to the framework, of course, but still, at least it's not blocking. The task combination, of course, is another nice thing you can have. The idea that you can now collect results and handle them in a synchronous or synchronous manner. For example, imagine I'm working in a platform team, and other teams make a request for the new API to be developed. And so they say, I first say, supply sync, team A, please file a request first. Then I say, team B, also file a request. And only after those two requests are filed, then I would combine the results of those requests and start processing. In this scenario, after two teams file the request for the API, I would basically combine them, evaluate the requests, and come up with a plan maybe for the next release or the next sprint. So this kind of a use case, you can see how you could have combined those two individual tasks and processed them. And last but not least, the exception handling is much better in the completable future comparing to the futures. Imagine again, I'm doing the crawler app. I'm trying to have a crawler service in place, but oh no, my website went down. Obviously, the crawling process would fail. A couple of calls I can make would be the exceptionally. The idea that it's similar to catch in try-catch statement. So that would be only triggered if the exception indeed happened. So you can either throw runtime exception, you can really interrupt it, or you can do some logging and send down the default value of some sort. Then there is also handle call, which basically is like finally, which would be similar to finally, but it's still a little bit different in the sense that it would be called regardless whether the exception was called or not. So if you basically have to check is throwable, non-null, and then handle it appropriately. As I've mentioned, you can do the default value, log it, process it, or just fail everything. So with that, I really have a call for action for you guys. As I've shown today, is really try to embrace concurrency, go away from this, trying to avoid it at all cost. It's not that old runnable threads that you have to avoid and hard to manage. Now you have more declarative model in Java that the entire framework is trying to move towards. Try to review your app. Maybe you can, even if you're still single-threaded app, as I've showed you, you can maybe still use the design for concurrency principles. And of course, continue, educating yourself on the, concurrent development. Nowadays, it's all about the reactive development, which is already, I think, made its way to the core Java libraries. So really don't stop, move on, go from this CompletableFuture, now look at the reactive programming. So again, don't stop there. It's great to see people going to the conferences, so I imagine you guys are interested in that stuff. So yeah, that's basically my call for action. And with that, I thank you. Thank you for joining me, and we'll go to Q&A. Thank you. Maybe I can kick off the questions that oh, you have a question? Great. Awesome.
How do you ensure that adequate unit testing is performed, that the code coverage covers all the exceptions and timeouts?
Exception. So that's two things, right? So code coverage, if you have what that famous code coverage thing called Jacoco, I think, it will still show the code coverage, the calls being triggered. So if you have that in that place, you would do exactly the same flows you have for the regular synchronous flow. So the same way you test your single-threaded application, you would have to. So that's all about the abstraction, right? So as I've mentioned with the design for concurrency, you try to abstract that logic, and just if you were to write unit tests, you don't have to spin off that multiple threads and try to hammer at it. First, obviously you try to test the operations, the work itself, in isolation from the multi-threading part. Obviously you have to trust. If you're wondering about the thread management, but you're using the executor service behind the scene, you can trust that. You don't have to worry about that part, of course. But if you're trying to test the multi-threading environment and how it's, if you have immutable states, that's a bit different concept. But I'm not sure if I answered the question. Is it clear to some extent? Because I said quite a few things.
Yeah. How to ensure that the various outcomes are all covered in a unit test, in an automatic unit test? I mean, when multithreading, it can happen in different threads. So the combination of that is difficult to obtain. So
obviously, I wouldn't do it on a unit test level. I would be worried about more end-to-end. So I would do a lot of stressed and load tests early on, because that would uncover pieces that you've missed, because off the bat, if this is a mutable object and I try to interact it from multiple threads, it's doomed to be affected at some point in time. So I really try to run it through maybe the stress and load test early on. But on a unit level testing, I would only tackle the operation that I'm executing as if it was a single-threaded. In other scenarios, as I've mentioned, if you're using the dependency injections, executor service, you never go with implementation, right? You always say executor service if you test it with a single-threaded factory that I showed you before, and then you can replace it with a cached thread pool if you wanted to. But to catch those scenarios you just mentioned, I would do stressed and load tests for the most part. Yeah. One thing I've been asked before quite a bit is CompletableFutures compatible with futures? Unfortunately not. You can't do it the same way, even though behind the scene they still use executor services, so you can pass down different thread pools. But unfortunately, they're not back compatible. You can't do the submit and just reuse futures in that regard. Yeah, that's a common thing I've been asked for. Any other questions? What?
Thank you, Dmitry.
Thank you so much. Thank you.